Electric flux is how much electric field is flowing through a given area. So if we have a flat rectangular surface which is in a constant electric field and you want to find the amount of electric field flowing through the area of the rectangular surface, in other words, you want to find the electric flux, you take the electric field through a very small portion and multiply it by the total number of small portions we have in the rectangle, which is the area. Mathematically, electric flux is equal to the summation of the dot product of the electric field and the small area vector. As the A approaches zero, this expression becomes an integral. Since the electric field is constant in this case, we can bring it out of the integral. The integral of the A is A, so flux of the surface is equal to the electric field vector times the area vector, which is E times A. Why do we have those arrows which represent vectors? It is because the direction of the electric field or area is important and we use only fields which are perpendicular to the area. So if this is a flat rectangular surface and this is the normal to the surface, the electric field must be parallel to the normal line. So what if we have an electric field that is not parallel to the normal? Then we have to resolve it to the normal, that is, find its component along the normal line. So if this is E, using SOHCAHTOA, here would be E cos theta. The flux would be E cos theta times A, where theta is the angle between the field and the normal of the surface. If theta is 0, cos 0 is equal to 1 and flux would be maximum. If theta is equal to 90, cos 90 is equal to 0, there will be no flux. If theta is equal to 180, cos 180 is minus 1, the field would be in the opposite direction. It would point inward. This is why inward flux from negative charges is negative and outward positive. We just dealt with the flux of a flat rectangular surface in a constant electric field. So now let's calculate the flux of a solid shape like a sphere. So if we have a sphere of radius r with a positive charge at the center, the flux would be the sum of the electric field over the total area. Therefore, flux is equal to the integral of the electric field times the A vector. Electric field is constant since all points on the sphere are at the same distance from the center. So we can bring it out and flux is equal to E times the integral of the A vector. The integral of the A is A. Resolving A is A cos theta, so flux is equal to EA cos theta. The A is perpendicular to the electric field from the positive charge because the electric field is radial and the radius of a sphere is perpendicular to each point on the surface. Therefore, the electric field is parallel to the normal of the A. So theta is 0, cos 0 is 1, flux is equal to E times A. From Coulomb's law, E is equal to Q over 4 pi r square epsilon naught and area is equal to 4 pi r square. Therefore, the flux is equal to Q over 4 pi r square epsilon naught times 4 pi r square. The 4 pi r squares cancel out, leaving Q over epsilon naught. Flux is equal to Q over epsilon naught. So we can use this simplified formula to get the flux of a sphere. But there is something so beautiful about the simplified expression we just got, that's Q over epsilon naught. Though I derived it for just this sphere, it works no matter the size of the sphere, whether it's a bigger sphere or a smaller sphere, or the shape of the surface, an irregular surface or a cube, or the position of the charge in the surface, so it doesn't have to be at the center. This is what Gauss discovered, that the electric flux flowing through a closed surface is equal to the charge enclosed divided by epsilon naught. And you're probably wondering how? Because the area would be different for different shapes and sizes. So why is the flux the same? So let me show you how it will be the same formula even if, let's say, the size of the sphere changes. Let's say our new radius is 2r. We know flux is E times A. E is Q over 4 pi r square and A is 4 pi r square. Substituting 2r for radius, flux is equal to E over 4 pi 2r all brackets square times epsilon naught, and A is equal to 4 pi 2r all brackets square. They are going to cancel out and we get, guess what, Q over epsilon naught. I can also prove to you that it will still be Q over epsilon naught if it wasn't even a sphere, that it will still be the same if it was any other shape like a cube or if the charge wasn't centered, but that's something that deserves a separate video. But let me give you a mental picture to calm your curiosity. So imagine that the number of lines represent the value of the electric flux. Here, 5 lines are flowing out of the sphere. If we change it to a cube, it's still 5 lines flowing out. And if the position of the charge is shifted from the center, still 5 lines would flow. In a similar way, the flux would be Q over epsilon naught, regardless of the size, shape, or position of the charge within the sphere. What if we had a charge Q outside the surface? Would the flux still be Q over epsilon naught? You can pause the video and try and figure this out yourself. Well, the answer is no, because the flux would enter the surface, that is minus Q over epsilon naught, and then leave the surface plus Q over epsilon naught. So the total flux would be minus Q over epsilon naught plus Q over epsilon naught, which is 0. So charges outside the surface do not contribute to the flux. That is why Gauss's law specifically says charge enclosed. That word is very important. If we had multiple charges inside the surface, the total flux would be the sum of the fluxes of the different charges. So, what is the point of Gauss's law? Yeah, it has a cool derivation, but what can we do with it? What can we apply it to in real life? It provides an easier way of calculating the electric field of surfaces with a particular kind of symmetry. These surfaces need to either have a cylindrical, a planar, or a spherical charge symmetry. By that, I don't mean that the surfaces must be a cylinder or a sphere, for their charge layout must have either of those symmetries. These kinds of symmetries, cylindrical and spherical, are called Gaussian surfaces, and they are actually imaginary, just like the orbit around the sun. We draw them around practical surfaces which possess the required symmetry, like a plain sheet of charge or a wire, to help us calculate the electric field. Why do we need the symmetry of a Gaussian surface? Because the symmetry makes the electric field constant, and so we can remove it from the integral and find it, which is actually the point of Gauss's law. I'm going to cover this topic, applications of Gauss's law, in-depthly in another video. So let's solve some problems on electric flux and Gauss's law. And I like to pick one hard and one easy problem because once you tackle the hardest, you can basically solve anything. So let's go. A point charge minus 2.4 microcoulomb is not at the center of a cube with sides L is equal to 5 cm. What is the electric flux through the cube? You can pause the video and try it out. So flux is equal to Q enclosed over epsilon naught, and the Q is 2.4 times 10 to the power minus 6. Epsilon naught is 8.85 times 10 to the power minus 12. That means flux is equal to minus 2.71 times 10 raised to the power of 5. So, what if the charge was outside? Well, you can pause and try it out. Well, the flux is going to be equal to 0 because it would enter, then leave. The next question, what if it was at the center of the cube? It's still going to be Q over epsilon naught, which is going to give you minus 2.7 times 10 raised to the power of 5. Then the next question, can we find the electric field using Gauss's law? You can try it out. No, because it doesn't have the symmetry required. Therefore, the electric field is going to be different at different points on the surface. So the second question, a constant electric field is 400 Newton per coulomb and makes an angle of 30 degrees with a square surface of area 4 meters square. What is the electric flux? Flux is the integral is equal to integral of E times the A. You can bring E out. So flux is E times the integral of the A, which is equal to EA cos theta. E is equal to 400 and A is equal to 4 meters square. So if this is the surface, then this is the field at 30 degrees to the surface. But theta is not equal to 30 degrees. We need to find theta, which is the angle the field makes with the normal. We can find it by doing 90 minus 30, which is equal to 60. Therefore, the flux is equal to 400 times 4 times cos 60, which is equal to 800 Newton meter square per coulomb. That's the unit of electric flux. Thanks for watching. Please subscribe. Always keep learning and always leave a question to be answered in your heart.